In this video, I'll be going over how to calculate the standard error. This is one of the key principles in statistical inference, is calculation of the standard error. It's really the sort of, if you want to think of it, the ruler which we gauge whether our sample is statistically significant. And so it's key that we learn how to calculate this and understand its meaning. It's also one of the most abstract concepts to understand, especially this concept of sampling distribution of the mean. Um, so before I go through and show you how to calculate the standard error in Google Sheets, I want to show you a visualization that is contained in this link that I'm highlighting right here. This visualization is great at helping us understand just what the standard error is. And so let's go to that now. So if we click on this link, we'll see a lot of sort of a graph and a lot of different options on the left. And I encourage you to spend some time playing around with this. I think it'll really help you understand the relationship between a population and a sampling distribution and a sample data set. So um, often what we're trying to do in statistics is have some inference about the population of individuals that we're sampling. And we form a, and as chapter 4 goes into, we form a hypothesis about our data. In this case, we're going to use a hypothesis that there is no that the population or mu is equal to 0. Now we're going to use this population distribution here to generate a sample of data. So this is what we're going to sample. We're gonna select a sample size that's it's got 20 observations, and our population mean is going to be 10, and our population standard deviation is going to be 10. So we know, because we're sort of playing the role of God here, statistical God, if you want to think of it that way, we know that our mu is not equal to 0. It's going to actually be equal to 10. But we're going to use this to kind of just illustrate the example. This is where our null hypothesis is, that mu is equal to 0. But because we're statistical gods, we know that mu is actually going to equal to 10. So, so so we're going to set this up where we have a bell-shaped distribution. As I mentioned earlier, our population mu is equal to 10, and our population standard deviation equal to 10, and we're drawing a sample of 20. We can select the number of samples we want to generate with each draw. We're only going to generate one sample at a time. So we're going to click right here on Draw Samples, and we get two new distributions here. So let's go into what these are. So this first one, this is the data distribution. So this is what you might generate if you're just a researcher and you draw a sample of 20 individuals and you measure their height, let's say, and you would get a data distribution like this. And so it looks kind of roughly normal in that it's kind of got a bell shape. There's this couple observations that are sort of outliers here. Remember our hypothesis that mu equals 0, and we get an x bar of 7.5. And this is where our null hypothesis is at 0. And so what we're trying to do here is have some inference. Is this x bar reasonable? Is it reasonable that it comes from a distribution that's centered at 0 or centered somewhere else? In this case, we know it's centered at 10, but our null hypothesis is the idea that this distribution, whoops, that's not quite, let's use that red line, is centered at 0 here. So that's what we're trying to infer here. And we're going to calculate the standard error as a metric to determine whether this x bar is sufficiently far away from 0. And so in calculating the standard error, we're going to use the standard deviation, 8.27, and the number of observations, 20. And we're going to plug it in to this formula that you see, whoops, where did it go? There it went. This formula right here, which is the standard deviation divided by the square root of the number of observations n. So we've drawn one sample here, and we're estimating the standard error. The standard error is basically an estimate of the standard deviation of the sampling distribution of the mean, and you can see that here. So the idea is that if we were to sample over and over and over again, if we were to do lots of experiments where we draw it from the same sample, we would get a sampling distribution of the mean. So each time that we drew a sample, we calculated the mean, and that is plotted here. So this first generation of sample generates a mean of 7.5. We can see that as the blue line down here, and we get just one observation here. So if we draw another sample, we get another observation. This time it's at 7.6, and that also is reflected down here. It's you just see one single bar because they're really close to each other. But we'll continue to draw samples, and we can see that as we draw samples, this X bar starts to kind of bounces around what we know the population mean to be, which is 10. And you can see that bouncing around here, what we know the population mean to be is 10. And we know via central limit theorem over repeated samples drawing 20 observations from this population over and over again, that this sample mean will approximate the population mean. And so we continue to do that, and we see that as we do that, this sampling distribution of the sample mean starts to resemble a normal distribution. It takes a little while. Some observations will be further away from the population mean than others, but as we get going, we'll start to see the it start to kind of look like a normal distribution. So if we click right here, we say let's just draw 1,000 instead of me clicking on this draw samples 1,000 times. We'll see that after 1,000 draws, that this sampling distribution, the sample mean, looks very close to the normal distribution. Yet each individual sample is going to have a lot of variability, both in its distribution shape. This looks kind of closer to uniform slightly, and also where that X bar, the sample mean is in relationship to the population mean. But we can see here that if we look at the mean of the sampling distribution, the sample mean, it's exactly the same as the population mean, even despite the variability from each sample. So what we're doing is we're estimating, when we conduct the standard error via the number of observations and the standard deviation, basically the standard deviation of the sampling distribution of the sample mean, and we're using that as a ruler or a metric to determine if this observation is sufficiently far away from where our hypothesis is in terms of our null hypothesis, which in this case we'd specified that as 0. So in this case, if we were to calculate the standard error, which we would use 8.9, and we use an n of 20. And let's go over here into Google Sheets. And I just opened up this. So here's our formula. Our standard deviation was calculated as 8.9, and we have an n of 20. I'm just typing these in. And this is our standard deviation. And we want to calculate the standard error. Actually, let's zoom in, make this a little bit easier for you guys to see. All right, let's move this over so we got a good, okay. So we're going to click equals to do some mathematical function. We're going to click on the cell that says 8.9. We're going to divide that, and we're going to type square root to get that function, and then we're going to put this cell that has the number of observations, and we'll close it off with brackets, and we get a standard error of approximately 2. Whoops, we'll round this. Let's just round this to the 100th. So we can look at now, if we go back to this observation here, remember our hypothesis was that this was 0 here, and we got an actual value of 12.4. So what I mean by using this as a metric, this will be in future videos, we'll see this in a little more close, but we've done this before when we calculate the z-scores. If we take 12.4 and we subtract it from 0, it's obviously just 12.4. So if we do 12.4 and we divide this by our standard error, this will be our z-score. And so 12.4 divided by what we calculate as our standard error, we get a z-score of 6.23. And this is how we're going to generate a p-value or a probability that this data comes from our null hypothesis. And because this is a very, very high z-score, I can tell you right now that the p-value will be very, very low, meaning that it's a highly unlikely that this data came from where our null hypothesis was, that the sampling, that our population mean was 0. And we know that the population mean wasn't 0. We specified it was 10. So hopefully this video this introduction to how the sampling distribution of the sample mean relates to the data distribution that we actually generate and the actual population distribution, how these three things interrelate, and how we make statistical inferences. This is the basis of all the statistical inferences that we'll be working on going forward here. All right, so now I want to show you how to calculate the standard error based on the data in the undergrad statistics characteristics data set. So we're going to come up with, we're going to go back to the data. Let's copy the first three big 5 personality factors variable names. Control C, or we can just go up here and write copy, and then we're going to go to their standard error worksheet that I created. We're going to put those variables, actually we'll move them over one, we'll put them here. And so the things that we need to obtain to calculate the standard errors, one, the standard deviation, and just the number of observations. So we're going to put our standard deviation there, or we'll put n here, and then we'll put our standard error right there. So to calculate the standard deviation of extroversion, we're just going to equals, then we're going to go back to the data spreadsheet. We'll click on column B, so we just select all the observations in column B, and then we'll hit enter, and we get a standard deviation, and let's give us a few more decimal points, of 55. Whoops, never mind, sorry. We're going to go equals, let me try that again, pull up the standard deviation, formula, let's just delete that, equals, pull this up, and then we'll go back to the data and we'll collect all the observations in column B that corresponds to extroversion. We'll hit enter. There we go. We get a standard deviation of 14.66. We're going to left click and drag over to the other two columns so we get the standard deviation for agreeableness and conscientiousness. And then we're going to we know the number of observations is 60. That's just the total number of observations. There's 60 persons in this data set, so that's the total number of observations. We'll just pull this over, and then our standard error, we're going to make a formula here, which is just this cell, which contains our standard deviation, divided by the square root. I'm just typing these into the keyboard. The total number of observations, we'll close that off with brackets. We get a standard error of approximately 1.89. We'll round to the 100th, and we'll drag this over to calculate the standard error for agreeableness and conscientiousness. So in this video, I've gone over kind of just some basics of sampling, how to conceptualize the standard error in terms of the sampling distribution of the mean, how that relates to the population mean and population distribution, as well as the actual distribution from the data that we gathered. I used a visualization. You can click on this and mess around with this to help you understand a little bit more. And then I also showed you how to use Google Sheets to calculate the standard error based on the data in the undergrad characteristics data set.